Hello and welcome back to another episode to Into KiTSiFOS. In today's video, I'm going to continue with designing the quad element setup with text input in my previous video. If you missed the previous one, go back and review it once more. At the end of the last episode, I reached the status where I run the linear analysis of particular load cases where I scaled the loads according to my needs. So in this video, I'm going to perform a design of the quad element based on the so-called Baumann method for load case 1. So the scaled load that can be seen here will be used in the design procedure. After the linear analysis done with module ASE, we need to define the reinforcement in the quad element. You can define the reinforcement of the quad element in module BMS as follows. First, we need to set up the geometry of the reinforcement with command geom, where you can set the h value, which is the height of the shell element. In this case, it is 400 millimeter. With the minus sign, I simply accept this value being taken over from the definition of the quad element. Then with the parameter HA, I'm defining the distance between the bottommost fiber and the center of the lower reinforcement in the principal direction. Then with the parameter DHA, I'm defining a distance between the principal reinforcement and the cross reinforcement. Similarly, with parameter HB, I'm defining a distance between the topmost fiber and the top principal reinforcement. And finally, with the parameter DHB, the distance between the top principal and the top cross reinforcement. In the next line with command dire, I'm defining the angle of the upper and the lower reinforcement. In this case, I set this value intentionally to 10 and 10 degrees just to see the effect of the angles of the reinforcement and how the transformation of the angles is being considered in the analysis. The last command in the definition of the reinforcement is the so-called para, in which you can define the parameters of the reinforcement group-wise. So with the help of parameter NOG, you can select the group on which you would like to define the parameters. If you enter a minus here, then it means that the parameters will be valid for all the groups. Then with the parameter du, you can define a diameter for the upper reinforcement. The value of this parameter is irrelevant in this case. What it matters is that it needs to be different from 0. By default, the very same value will be assigned to the lower reinforcement diameter as well. After having finished with the definition of the reinforcement, we can undertake the design of the shell element in a next BMS run. If I scroll down, you can see that I have already created the input for the design. So in a new BMS module, you need to instruct the software to design the shell element as follows. First, with the command control, you need to instruct the software what type of design you would like to perform. You can add it in parameter type, and as you can see, I have entered ULTI, which stands for the ultimate limit state design. With parameter lay0, I have just chosen the method to be used. Because BMS is capable of using two different types of methods, with value 0 at parameter lay, the software will use the so-called Baumann method, whereas if I entered lay1, it would mean that the software will use the so-called layer method. Then with the parameter LCR11, I'm storing the increased reinforcement in the distribution number 11. As you remembered, in module SOFiLoad, I have created a new load case with number 1, into which I have copied in the different unit loads and multiplied them with a factor respectively. Finally, with the command lm101, I am selecting the element to be designed. In this case, I have only one element with number 101. Okay, now let's quickly run this model and see the results in the report browser. This simple analysis calculated through very fast, so I'm just going to open up the report and check the result in the last BMS run, for example, the required reinforcement. In the table, we can see that the software calculated the required reinforcement amount 13.51 centimeters square per meter in the lower principal reinforcement layer and 11.94 centimeters square per meter in the lower cross reinforcement layer. Please notice that there is no reinforcement necessary for the upper layers. In the below table, we can see the detailed results of bending and the shear design. But what I would like you to remember from this table is the thickness of the shell element, which is 400 millimeter. The lever arm for the upper reinforcement was calculated as 306 millimeter. And also the very same value can be seen for the lever arm of the lower reinforcement. So these are the values that I try to verify, especially the required reinforcement with my hand calculation. So now I will try to explain the underlying theory of the design procedure, which is based on the so-called Baumann method. The main concept of this method is to subdivide the shell element into so-called panels or disks. So there is a top panel in the shell element, a middle core, and a bottom panel in the shell element. Besides, the shell section is subjected to a membrane stress and a moment stress, as you can see in this picture. What we are going to do is we are going to decouple the moment into a pair of forces that are acting in the top and bottom panels. And also we are going to divide the membrane force into the top and bottom panels. Finally, we are going to receive or get a system in which we have only membrane forces acting in the top or bottom panels. These two membrane forces are then used to determine the design forces and the required reinforcing. Let's assume that there are two layers of reinforcement, that is the top layer and the bottom layer reinforcement in the two principal directions. First, let's see the verification of the lower reinforcement in the bottom panel. In my example, the bottom fiber of the shell element is in tension. The internal forces of the quad element that can be seen here was copied over from the example file to be able to verify the output of the report browser. So from the given internal forces of the quad elements, the principal bending moments can be calculated or assessed as per the formulas that can be seen on the screen. So basically we are taking the MXX, MYY bending moments and the MXY bending moments and calculating the principal bending moment. And similarly the other principal bending moment. Then we also need to calculate the principal normal forces and the angle in between them. The formulas are very similar what we saw for the principal bending moments. Then we need to determine the lever arm of the internal forces. The lever arm is calculated from the internal forces in the principal moment directions and in the principal normal force directions respectively. That is why it was very important to assess these values. This procedure is undertaken according to a so-called KA procedure that is very well known in Germany. At the end of this iterative procedure, the program chooses the most unfavorable lever arm and uses in the forthcoming analysis steps as the lever arm Z. I will scroll down a little bit and show you the concept of this KA procedure. As I mentioned, it is an iterative procedure, so based upon the given internal forces, the angle of this strain plane needs to be found, because if we know the inclination of this strain plane, then we can calculate the x value and the z value, the lever arm, very easily. Please notice that in this procedure, the nonlinear workflow of the concrete will be used. As we saw in the report browser, the software calculated with this iterative procedure 0.306 meter, and now I will briefly show you how it was calculated. So from the parameters of the concrete material and steel material, and also from the properties of the cross-section and the acting internal force, the strain plane will be calculated with the iterative procedure, and the strain in the concrete is calculated, and also the strain in the steel. From it, we can calculate all of the necessary parameters that we need based upon which part in the workflow we are. If you can see, if we are at the parabolic part of the workflow, then these formulas needs to be used. Whereas if we are at the constant part of the workflow, other values need to be used. When I try to calculate the iterative procedure, I receive 0.308 meter, which is very similar what the software calculated as 0.306 meter. Okay, if the lever arm Z is calculated, then it is used to calculate the virtual panel force in the direction of the element's local coordinate system on each side of the finite area element. In other words, what we are doing in this step is to decouple the bending moment into panel forces and also subdivide the membrane forces into the panels. As you can see, the membrane forces are simply divided into two parts, into the two panels, top and bottom, and the membrane force is divided with the lever arm. This is the way how we can get the panel force in the local x direction of the shell element. Similarly, we subdivide the NYY membrane force into two parts, top and bottom panel, and calculate the pair of forces from the MYY bending moment with the help of the lever arm. The NXY membrane force is calculated by dividing the NXY membrane force into two parts, plus the MXY bending moment divided by the lever arm. Okay, now the next step is the transformation of these local panel forces into principal panel forces. The following formulas are used to calculate these principal panel forces, and it is also very important to calculate the angle between the principal panel forces. Here what you can see, the angle is minus 10.3322 degrees. And now I would like to explain what direction this means. So basically this Vn is the angle between the local x-axis and the principal panel force. Let's assume that the local coordinate system of the shell element is as presented. So the local x-axis pointing to the right and the local y-axis pointing downwards. So a positive angle of Vn turns the coordinate system of the principal panel force in the direction of the local y-axis. So basically clockwise. Therefore, the Vn being equal with minus 10.3322 degrees, meaning that the direction of the principal panel forces is something like this. However, the angle of the main reinforcement was set to 10 degrees in my input, so it is pointing in this direction roughly. The overall angle between the principal membrane force and the reinforcement is 20.3322 degrees. In the below picture, I am presenting the direction of the principal reinforcement, and as I mentioned, the angle of the principal membrane force is minus 10 degrees, so basically somewhere here. The next step is to calculate a quotient of the principal panel membrane forces. Because this quotient needs to be compared with this expression, since according to the Baumann method, if the quotient is greater than this expression, then the formulas on the left side must be used. Whereas the quotient is smaller than the expression, then other formulas needs to be used. In this example, I need to follow the left branch. So the next step will be to calculate the tension force in the reinforcement in the principal reinforcement direction. So I have entered the formula from the Baumann method and I received 1474.5 kilonewton per meter, which is matching with the output of the report browser. Similarly, I had to calculate the tension force in the cross reinforcement, which was undertaken according to the formula from the Baumann paper. And as you can see, I received 534.1 kilonewton meter, which is again matching with the output of the report browser. However, as you can see, there is a value at layer 3, and more precisely, a negative value. What is this value? As you can see in the bottom panel, I have two tension forces. In order to maintain the equilibrium, a compression force must act in the bottom panel as follows. Again, I can either use the formulae from the Baumann paper or simply analyzing the equilibrium in the panel, and I will receive this 807.9 kilonewton per meter, which is again matching with the output of the report browser. After having calculated the panel forces, now we can assess the necessary amount of reinforcement as follows. We just simply need to divide the Z1 value with the sigma SD, where the sigma SD can be derived from the steel tensile stress divided by 1.15. In my hand calculation, I received 30.7 centimeters square per meter necessary amount of reinforcement, and from the report we can see 30.5 centimeters square per meter is required, which I think is a quite good match. If I scroll down, you can see that I calculated the necessary amount of cross reinforcement in the very similar manner. Simply divided the Z2 value with the sigma ST and received 11.13 centimeters square per meter, which is again a quite good match with the report browser output. Okay, now we are finished with the bottom panel, but what about the top panel? For the verification of the top panel, again we are going to need the lever arm, which is in this example file equal with the lever arm for the lower button. And later on we will need the corresponding height of the concrete compression zone, x equal 41.2 millimeter. But the most important thing is how to calculate the panel forces. If you remember, for the bottom panel, we simply divided the NXX forces into two parts and added the MXX bending moment divided by the lever arm. However, in this case, we need to deduct this part, since we are using now the other element from the pair of forces derived from the bending moment. Similarly, for the NYY bending moment, we need to subtract the MYY over the lever arm part. And the same is applicable for the calculation of the NXY. And as for the bottom panel, now the next step for the top panel is to transform of the local panel forces into the principal panel forces with the already known formulas. In this case, I have received negative values both for N1 and N2. And since both of the principal panel forces are compression force, there is no need of any reinforcement for the concrete if the concrete can resist this compression stress. So let us quickly calculate the design compression stress in the concrete. Simply, we need to divide the N2 over the compression height of the concrete, which is x, and we are going to get negative 20.8 Newton per millimeter square, which is smaller than the resistance of a C45 concrete, as you can see. So really, we can conclude that we do not need any reinforcement in the top panel, and this is matching with the output of the report browser. As you can see, this is the top panel force, and the table doesn't show any necessary amount of reinforcement for the top panel. Okay, so now I reached the end of my verification, but I would like to give some hints regarding the design. Please notice that the effect of the vertical shear, the Vx and Vy, was not considered in this method. The necessary amount of shear reinforcement in the shell element is calculated as a regular beam, so the Vx and the Vy shear forces will be simply divided with the lever arm calculated for shear, and based upon the stress, the necessary amount of shear reinforcement can be calculated. If someone would like to consider the effect of the vertical shear forces Vx, Vy in the design of the longitudinal reinforcement of the shell elements, then the so-called shift rule must be used, which can be activated in module BMS with the command shft referring to shift, and if the value is given as 1, then the shift rule will be considered according to Eurocode 2. And this is the way how you can consider the effect of the vertical shear forces in the design of the longitudinal reinforcement of the shell elements. With this information, I am concluding this video. Thank you for watching it, and I'm going to torch you in the next one very soon. Bye bye.